Hey guys, we're going to be looking at our continued stuff on conditional probability, but this time we're going to be looking at the actual equation itself, the formula that we tend to direct ourselves to from now on. All right, we've got our probability of A given B. When we have this situation, the sample space for the rest of this probability is restricted just to B. That means that our total becomes the probability of B. And on the top line, if we're considering the probability of A given B, then we're thinking about A is happening and B happening. So the probability of A and B happening out of a total of the probability of B is what's occurring. We can even think about this as a Venn diagram. So if that was A and this is B, we're looking at the probability of this part out of the total of B. So it makes up a small fraction of that A and B out of B. So, as I said, probability of B restricts the sample space. From there, if we were to multiply both sides by the probability of B, it gives us our multiplication rule. That is that the probability of A and B occurring, which is that top line up here, is equal to the probability of A given B times by the probability of B. And you might consider that this is something that we've been doing for our tree diagrams already. This is what the branches at the end have made up of. In fact, what I'll do is I'll show an example. So, probability of 2 greens here, we had 5 marbles, 3 are green, and then when we took one out, probability of getting a second green now becomes 2 out of 4. So the probability of both occurring, green and then a second green, is probability of green given the first is green is 2 out of 4, and that's that part of my tree diagram, and then times by the probability of the first green. Okay. Same as our multiplication. So for independent events, the probability of A given B is just the probability of A. So this changes our multiplication rule. The probability of A and B happening is that it's just the probability of A times by the probability of B. We'll go through a quick example here, but again, we're going to do more of this a little bit later. We've got flipping a coin and rolling a dice. So if we're looking at the probability of rolling a 3 and getting a head, okay, rolling a dice and flipping a coin are two independent events. The coin result doesn't change what's happening on the dice. So we can split this up. Probability of both happening is the probability of each one separately happening multiplied together. Probability of rolling the 3 times by the probability of head is 1 over 6 times by 1 over 2, and that's 1 over 12. There's one option to get a 3 and a head out of the 12 that there are. And you could do a two-way table if you wanted to show that that's definitely true. So we're going to come back to independence next time. Let's talk more about this conditional probability stuff. We've got 3 cards are taken from a normal 52 card deck. What is the probability of 3 kings given 2 kings? And you might remember questions like this back in the tree diagram exercise we did a little while back. Okay. If 2 kings have already been drawn from the deck, how many kings are left? Well, there's 4 of each kind of card. So if we've taken 2, sorry, let me make that slightly clearer. Taken 2, and then how many cards are left? 2 out of 50. So that's one idea of our conditional probability, and that's one that we can just think through a little bit. go to another example. What is the probability of 2 jacks in the first 2 cards from a well-shuffled deck? Now you might use a tree diagram. Okay, we'll come back to that. In fact, it's already here if you wanted to look ahead. But just for now, ignore this part. So we can just think through this problem. If we're looking at the probability of 2 jacks from a 52 card deck, its probability of getting a jack and a second jack. So because the first jack affects the second, we're looking at the probability of getting a jack given that the first one's jack, and we're going to multiply that by the probability of the first one being a jack. So again, there's 4 of a kind in a deck of cards. So there's 4 out of 52 originally, and then when we take one of the jacks out, we've only got 3 left out of the 51 cards. Multiply those two results together, and we get about 0.45%. So we could go back to our tree diagram just in case as a way to explain what's going on here. We're looking at the probability of getting a jack, which is 4 out of 52, and then a second jack. All right. This is the probability of getting a second jack given that the first one is a jack, because that's had an impact on this. So the probability of getting 2 jacks, both of those branches of my tree diagram, which is 4 over 52 times by 3 over 51, just like we would have seen in our previous exercise. And then our last example, we're actually going to use the conditional probability formula. Okay. In Australia, the probability of having blue eyes is about 35%, and the probability of having natural fair hair is about 22%. Probability of having blue eyes and fair hair is about 6%, and we're trying to find the probability of having blue eyes given that they have fair hair. Now, conditional probability, that fair hair has become our new total. So it's probability of having fair hair. Fair hair is about 22%. So 0.22, or whatever you'd like to write in there. Out of that 0.22, how many have blue and fair hair? Okay, probability of having blue eyes and fair hair is about 6%. Just in case, blue and fair over the probability being fair. And this comes directly from our conditional probability formula. Probability of having blue eyes given fair hair is equal to probability of blue eyes and fair hair over the probability of fair hair. Same situation. And then lastly, we're looking at the probability of fair hair given that they have blue eyes. So then the blue eyes is going to be the new total. So out of the probability of getting having blue eyes, which is about 35%, probability of having both fair hair and blue eyes, both of these, is again 0.6, and sure we can calculate those on our own, but probability of fair, can't spell fair, and blue eyes over the probability of having blue eyes is where this is coming from. Alright, I hope that helps. Let me know if you've got any questions.